Okay. I will send out the chapter 3 exam shortly after class. I'll let you work on that till midnight Friday night. Give you a little bit more breathing room. So you can turn it in by midnight Friday night. I'll email you and confirm that. I will also indicate what precisely I want you to turn in for your chapter 3 textbook homework. You can turn that in also by midnight Friday night. And so that's what we'll do with that. Okay, we're going to begin a new chapter today, chapter 4, as we are about halfway through this course. In section 4.1, we are going to begin to look at the graphs of our basic trigonometric functions, the sine, the cosine, etc. If you have your graphing calculator this morning, just have it handy, as I will show you how we can graph on our calculator. And I'll also obviously go over how we would graph in a manual sense these functions here. We're going to discover that these functions are periodic in nature. And the reason why they're periodic in nature is because they take their input values from the unit circle. And so you might want to have that unit circle also handy for today's lecture that we developed on Monday. That'll expedite our ability to graph these things manually. So as we go around the unit circle, we input values into the trigonometric functions in order to get the output y values. And because we go around the unit circle, ladies and gentlemen, there's really, theoretically speaking, there's no end to how many times you can go around the unit circle, both counterclockwise and clockwise. And because of that, the graphs of these trigonometric functions could extend indefinitely to the right and left in the XY plane. Because stop and think, remember what I said, every angle has an infinite number of what? Coterminal angles. Do you agree? In other words, a 30-degree angle, what would be a coterminal angle to 30 degrees? That would be 390 degrees. 750 degrees, do you agree? Would be coterminal to 30 degrees. Negative 330 degrees would be coterminal to 30 degrees. So there's really an infinite number of coterminal angles for any angle. And because of that, we're going to see these graphs repeat in a cyclical fashion, if you will, because all of them are periodic. In fact, all of them are 2 pi periodic. Okay, so here we go. In fact, ladies and gentlemen, I think it's better today, as far as the lecture is concerned, it will be more elegant if I go over a PowerPoint presentation. I will attach that PowerPoint presentation to Canvas for your viewing later on. I mean, the pictures are nicer, they're in color, they're just so much better than what I could do on paper. So it is a brief PowerPoint presentation. All right, so here we go. Hopefully all systems are working. All right, so section 4.1, we are going to learn how to graph our trigonometric functions, okay? Now, here is a table, ladies and gentlemen, that has input values for X in the first column. And all of these values are not in degrees, but they're all in radians, notice. The second column is the function that we are going to focus on. It's the basic sine function, y equals sine x. The third column then will represent the ordered pairs that will ultimately lie on the graph of y equals sine x. So in essence, we are going to graph this trigonometric function y equals sine x. First of all, can we all see this table? Is this table visible?
Yeah, I can see it.
Okay. Just want to make sure I got my screen sharing on. One time I went through about half the lecture and I forgot to do screen share and nobody drew my attention to it. So, okay. All right. So here's what we're going to do, ladies. It's really a fairly simple matter. Now, do we have that unit circle handy by our side that we developed on Monday? With all the ordered pairs around as points around the unit circle. Do we have that? That really would help, unless you got all these memorized, and that's even more power to you if you do. But anyways, ladies and gentlemen, if you let x be 0, you put 0 in for x into this sine function, what would you get out? Well, what's the sine of 0 radians? The sine of 0 radians would be 0. Do you agree? And so therefore, one ordered pair that will lie on the graph of y equals sine x will be the ordered pair 0, 0. So the graph of sine x contains the origin point. If x is pi 4th radians, you put pi 4th radians in for x. And ladies and gentlemen, check your unit circle. What's the sine of pi 4th? Remember, the sine of the angle is the y coordinate of the point that's labeled on the unit circle. What's the sine of pi 4th? Confirm for yourself that the sine of pi 4th radians is the square root of 2 over 2, or 1 over the square root of 2, which is about 0.7 approximately as a decimal. Hence, another ordered pair that would lie on the graph of y equals sine x would be pi 4th comma 0.7. Onward we go. If x is equal to pi half radians, what's the sine of pi half radians, or the sine of 90 degrees? Well, that's the point that's up there on the y-axis, that point 0,1, the y coordinate of which is 1. So the sine of pi half radians is 1. Hence, pi halves comma 1 would be another point that would be found on the graph of y equals sine x. Now we go to 3 pi 4th radians. The sine of 3 pi 4th radians, which is really the sine of 135 degrees, is again 1 over the square root of 2 over the square root of 2 over 2, or about 0.7. So 3 pi 4th comma 0.7 would be another point found on the graph of y equals sine x. Pi radians is 180 degrees. So the sine of pi, or the sine of 180 degrees, is that point on the x-axis to the left, which is -1, 0. And since the y coordinate is 0, the sine of pi radians is 0. So pi comma 0 would be another point found on the graph of y equals sine x. 5 pi 4th radians takes us into the third quadrant. That would be 225 degrees. The sine of 225 degrees, or 5 pi 4th radians, would be negative square root of 2 over 2, or negative 0.7. Hence, this would be another point found on the graph of the sine function. The sine of 3 pi half radians, which is the sine of 270 degrees, that's a quadrantal angle. That's the point on the y-axis that's down below on the y-axis. That would be the point 0, -1. And so y would be -1. So the sine of 3 pi half radians is -1. Hence, this ordered pair would be a point found on the graph of y equals sine x. 7 pi 4ths takes us into the fourth quadrant. That would be, well, how many degrees is 7 pi 4ths? Anybody? 7 pi 4ths radians. What is that?
315 degrees.
315 degrees. That's in the fourth quadrant. And the sine of 7 pi 4ths, or 315 degrees, would be negative square root of 2 over 2, approximately negative 0.7. Hence, this point would also be found on the graph of y equals sine x. Finally, 2 pi means that we've completed one circuit around the unit circle. We've gone around one complete time. 2 pi, of course, is coterminal with 0 radians, or 360 degrees, or 0 degrees. And the sine of 2 pi radians, we're back to the quadrantal angle of 360. So that's the point 1, 0 on the x-axis, the y coordinate of which is 0. So the sine of 2 pi is 0. And 2 pi comma 0 would be a point found on the graph of y equals sine x. Okay. Notice the scaling that's used on the x-axis to graph this sine function, ladies and gentlemen, is what? The tick marks are spaced. How many units apart are these tick marks spaced? Anybody?
45 degrees.
45 degrees, or in radians, we would say what? They're spaced
Pi over 4.
5/4 radians apart. Notice, look at 0 pi fourths, 1 pi fourth, 2 pi fourths, but 2 pi fourths is really pi halves. 3 pi fourths, 4 pi fourths, but 4 pi fourths is pi. 5 pi fourths, 6 pi fourths, but 6 pi fourths is really 3 pi halves. 7 pi fourths, and then 8 pi fourths, which is better known as 2 pi. So these are separated by pi fourth units. Does anybody want to comment on the range of this function sine x? In other words, the range of the function is the minimum value found in the range versus the maximum value. In other words, the minimum value of y that this function ever assumes throughout the values of the domain, and the values in the domain of this function are 0 to 2 pi. Okay. So what's the minimum y value output of this sine function? The minimum y value. You know what? We don't, just kind of looking here. Yeah, what's the minimum y value do you see, ladies and gentlemen, that was output by this sine function?
-1.
-1. And what was the maximum value for y?
A whole 1.
+1. So look at the range of this sine function is from -1 to 1. Okay. So let me show you what's going on here. So the domain of this function is 0 to 2 pi. This is called interval notation. The brackets indicate that the endpoints are part of the set or part of the domain or are in the domain. So the domain of this sine function ranges from 0 to 2 pi, and the range of this sine function is from -1 to +1. All right. So when we graph this sine function here, y equals sine x, all right, the input values are any decimal radian measurement that lie between 0 and 2 pi inclusive. The range values or the output values of the y equals sine x function are any decimals between -1 and 1. And obviously there's an infinite number of decimals between 0 and 2 pi in this interval, and there's an infinite number of decimals between -1 and 1. Okay. And for that reason, when we graph the y equals sine x function here, we're not just going to see the plotting of a couple of points. Ladies and gentlemen, what we're going to see is we're going to see a smooth curve. Hold on a second, connecting all these points. But nonetheless, we cannot plot an infinite number of points because we would be here till the end of time. And so these are the nice points that we've chosen to plot in the XY plane. So let's go ahead and plot these points. And after plotting those points in that table that we just seen, then connecting them with a smooth curve here, ladies and gentlemen, you can see that you have the graph of one cycle or one period of the sine function. Now, why do we call this one cycle or one period? Well, we call it one cycle or one period because, ladies and gentlemen, we started with an input value of 0, and then we went to pi fourths, 2 pi fourths, 3 pi fourths, 4 pi fourths, 5 pi fourths, 6 pi fourths, 7 pi fourths, and then 2 pi. We made one complete trip around the unit circle, one cycle around the unit circle. And for that reason, you are looking at the graph of one cycle of y equals sine x. Okay. Notice the highest point on this graph, in other words, the point that possesses the maximum y coordinate occurs right here when x equals pi halves. That's when y is equal to +1. The lowest point on this graph occurs when x is equal to 3 pi half radians. Y in that case is equal to -1. Okay. All righty. Below here is the graph of let's see something here. Below here, ladies and gentlemen, is also a graph of y equals sine x. It's just that now the x-axis has gone from a scale where the tick marks are spaced pi/4 radians apart to now where they're spaced how many radians apart? What's the scaling used on this axis down here? This x-axis. How far apart are these tick marks spaced on the x-axis down here?
Pi/6.
I'm sorry, you
Four.
can't see my cursor. Yeah, sorry about that. On this x-axis down here, notice these tick marks are spaced pi/6 radians apart. 1 pi/6, 2 pi/6, which is really pi/3, 3 pi/6 reduces down to pi/2, 4 pi/6 reduces down to 2 pi/3, 5 pi/6, 6 pi/6 is really pi, 7 pi/6, 8 pi/6 is really 4 pi/3, 9 pi/6 is really 3 pi/2, 10 pi/6 is 5 pi/3, 11 pi/6 and 12 pi/6 is 2 pi. So the only difference between the graph on the top and the graph on the bottom here for y equals sine x is that the graph on the bottom, the x-axis has a finer resolution as far as its scaling is concerned. In other words, more points were plotted on this graph below as opposed to the graph above. Okay, but nonetheless, the graphs are still identical because they still represent one cycle or the graph of one period, we say, of y equals sine x. All right, does that make sense there? All right, let's see how we can graph on this sine function on our calculator. So let's bring up the machine. And ladies and gentlemen, when we graph trigonometric functions, we're usually always in radian mode because the input values are radians and not degrees. So hit your mode button. Make sure your calculator is in radian mode. Notice mine is, so I'm good to go there. The next thing you want to do is hit your window button. At the top of your keyboard, you have a button that says window. And this is where you can configure how you want your x-axis and y-axis to be laid out. So to graph the sine function here, y equals sine x, let's have our x minimum value start at 0. And let's have our x maximum value be what? What are we going to have our x maximum value be? Anybody? We always ran from x equals 0 to what for those graphs? 2 pi?
2 pi.
So here's what we type in. 2, for x max, we type in 2 and then go get pi, second power button, pi. So our x-axis is going to range from 0 to 2 pi. And the tick marks, the x sub SCL represents the scaling you want to have on your x-axis. Suppose we want our tick marks to be spaced pi/6 units apart. So we would go get pi and divide that by 6. So we want our tick marks to be spaced pi/6 units apart on the x-axis. Hit enter. Notice those are converted into decimals. The range of this sine x function we've seen was from -1 to 1. So we want our y min value to be -1 and our y maximum value to be +1, because the output values of this sine x function are never going to be any values less than -1 or greater than +1. The scaling we want on our y-axis is kind of arbitrary. I chose 0.5, so my tick marks will be spaced 0.5 units apart, or you could choose a finer resolution, say like 0.25, or a very, very fine resolution to say 0.01. Okay, whoops. So it's up to you. I'm just gonna go back to 0.5 though. Resolution, I just leave as 1 always. I don't mess with that. And the change in X, I never really bother with that. We don't have to worry about that. All right, here we go, ladies and gentlemen. So let's hit our graph button now. And you should see the graph of one cycle or one period of y equals sine x. Do we all see that graph on our calculator? Anybody in here that does not see that graph?
I did not get.
Well, of course you don't see it because we didn't do something, and I apologize. I forgot to go to y equals, ladies and gentlemen. We got to type in the function we want to graph. So hit y equals, and you need to type in sine x. So you hit your sine button, and then you hit your X button. Your X button is just to the right of your alpha key, this X comma T comma alpha comma theta comma N. Just hit that button. That will be the input argument into the sine function or the independent variable X. Hit the closed parenthesis, hit enter. Now, ladies and gentlemen, when you hit graph, do you see the graph of one cycle or one period of the sine function? Do we see it now?
There it is.
Does that appear now, Sean?
Yes, sir.
All right, Jared, do you see that?
Yes, sir.
Trent, do you see it?
Yup,
Mark Brooks, do you see that graph?
I see it. Yep.
All right, anybody in here that does not see this? Okay, that is the graph of one cycle or one period of the y equals sine x function. Ladies and gentlemen, if you hit your trace button at the top of your keyboard, you see a button that says trace. If you hit trace, and then you use your right or left arrow key on your keypad, you can walk along that graph, and you can see the ordered pairs that correspond to location of that little cursor there on the bottom of your screen there. Okay. You see that there? So you can always walk along the graph. Ladies and gentlemen, whenever you graph a function on your calculator, behind the scenes, a table is always created. So if you hit your second button, followed by your graph button, that will take you into your table. Second graph takes you into your table. Your first column represents input values into the function y equals sine x. Your second column represents corresponding output values. So the sine of 0 is 0. Okay. Now notice my x values are changing by 1. I told my calculator to graph it where my x values change by pi 6. So here's what you can do. If you want these x values in your table to be changing by pi 6 radians instead of by 1s, you go to your table setup mode. Above your window button is the word table set. So to access it, we hit our second key followed by our window button. We'll tell our calculator we want our x values to start at 0. We'll tell our calculator we want our x values to change by pi 6 radians. So we type in pi divided by 6 here. The change in the table values, that little triangle represents the word change in mathematics. You'll see that a lot in calculus, your first semester. The change in your table values or the change in your x values, we want to be pi 6. Make sure your independent and dependent variables are on both auto, not ask, but auto. Now, ladies and gentlemen, when you go to your table, second graph, you'll see your x values start at 0 and they will increment by pi 6 radians. So the sine of pi 6 is 0.5. The sine of 2 pi 6, which is pi 3rd radians, is about 0.8603. The sine of 4 pi 6, 0, 1, 2, 3. The sine of 3 pi 6 radians, which is the sine of pi half radians, which is the sine of 90 degrees, is 1. Okay, and so you can scroll both downwards. Notice this is the sine of 2 pi, and the sine of 2 pi is 0. Or you can scroll upwards with these X values and look at the corresponding output values of Y equals sine X. So you can go backwards too. You see that? Negative angles. There's negative 2 pi. So the sine of negative 2 pi being coterminal to 2 pi or 360 degrees or 0 degrees is 0. So the sine of negative 2 pi is 0. All right. All right. But we told our calculator, ladies and gentlemen, to graph only one period or one cycle of Y equals sine X. Here's another nifty thing you can do. You can also have your calculator search out and find maximum points on your graph or minimum points. How many people have ever done this using your graphic calculator in college algebra? Anybody do that in college algebra with the calculator?
I think I did, but I'm having a foggy memory of it.
Okay, college algebra at Mott Community College is Math 130. And in Math 130 college algebra, they use the TI-84 graphing calculator extensively. They should. And they should show you how to find max and mins on the graph. To find the maximum point on this graph, here's what you do. You go to, see, go to, that's not it. Hold on a second here. You go to calculate, ladies and gentlemen. So you got to hit your second button followed by your trace button to get into calculate. Second trace gets you into the calculate mode with your graph showing. So with your graph showing, you go to calculate mode, second trace. Now you go down to the maximum function here. So let's select the maximum function by hitting enter. And now, ladies and gentlemen, what you need to do is you need to box in the maximum value you wish to find using your calculator. What does that mean? Box it in. Well, let me show you what that means quickly here. To box into this maximum point, ladies and gentlemen, your calculator wants you to establish a left bound. So you have to move this blinking cursor on the graph so that it's a little bit to the left of the high point. Your calculator will then establish this as a left bound. Then your calculator will want you to establish a right bound where you navigate the blinking cursor just to the right of that high point. Here's your blinking cursor. Your calculator will then establish this as being a right bound. Your calculator needs to box in this maximum point we wish it to find in order to go through a numerical routine behind the scenes very quickly, ladies and gentlemen, to find that maximum point. If you get into numerical analysis someday, you'll discover exactly what routine or algorithm is being used to zero in and pinpoint that maximum point. Okay, so here we go. So ladies and gentlemen, to establish a left bound, I need to navigate my blinking cursor so that it's to the left of that high point, somewhere to the left. It doesn't matter where you put it to the left. You know, just put it in the local vicinity, somewhere to the left of the high point. Hit enter, and notice your calculator now wants a right bound. So now we have to, using our right arrow keypad, we have to navigate this blinking cursor so that it's somewhere to the right of that high point on the graph. I'll put it about there. Hit enter. Your calculator now has established a right bound. Now, when your calculator says guess, we just hit enter again. Your calculator went through that iterative routine very quickly behind the scenes. And ladies and gentlemen, you can see the maximum point occurs on this graph at x equals 1.5707979 radians. Does anybody know in exact form what radian measurement is 1.5707979 radians?
I'm assuming it's pi over 2.
Pi halves, exactly. So the maximum point on this graph occurs at the point x equals pi half radians and y equals 1. So pi half radians comma 1 is the maximum point on this graph. In a similar fashion, to find the minimum point down here, again, we can go to calculate mode, second trace, and go down and grab the minimum function. It works very similarly as the maximum function. We have to establish a left bound, so we have to navigate our blinking cursor in the vicinity of the point we wish it to find, and make sure you have it a little bit to the left of the low point. Hit enter. Now your calculator wants a right bound. So now you navigate the blinking cursor so that it's a little bit to the right somewhere on the graph of the low point, somewhere in there maybe. Hit enter. See what's happening? Your calculator is boxing in this low point within an interval. Hit enter again, and after a fraction of a second, your calculator zooms in and finds that minimum point. And this would be the radian measurement for X where it occurs, 4.7123884, which is in exact form 3 pi half radians, right? 3 pi half radians. And that and Y then would be -1. So the sine of 3 pi half radians is -1, and that's that low point down there. Now we really can't see, ladies and gentlemen, this low point very well because I told my calculator to have the y-axis run from -1 to 1, but we can simply adjust this a little bit if we go to our window setting. Leave X alone, but have your y-axis go from like -1, -2, let's say, to +2. That'll give us a little more breathing room as far as the vertical is concerned with the graph. Hit graph now, and now you can see we still have the graph of one cycle of our sine function, but notice the x-axis now goes from -2 to 2. So now it'll be much easier to see, you know, this minimum point when you go to calculate and find it. There will be a left bound, and now I need a right bound. Right bound, hit enter, and there's the minimum point, 3 pi half radians -1 down there. Okay, so pretty neat how you can do the graphs on the calculator. Even look at table input value, table input and output values. You can find max and mins on your graph. Okay, so a whole bunch of good things you can do there. So have some fun with this calculator. You know, the only way to learn how to use it is by just, you know, spending some time with it. Okay, so let's get away from y equals sine x. Now, ladies and gentlemen, since we have the graph of one cycle or one period of y equals sine x, we can use this graph to answer some questions. For instance, suppose we use the graph of y equals sine x here to find all values of x between 0 and 2 pi for which the sine of x is equal to 1/2. Well, I know if you take a horizontal line and you have it touch the tick mark on the y-axis at 1/2, and you draw that horizontal line from left to right, okay, it's the point of intersections between the horizontal line and the graph of y equals sine x that will answer this question. So for what x values is the sine of x equal to 1/2? Well, you can see that occurs when x is equal to pi/6 radians. When x is equal to pi/6 radians or 30 degrees, the sine of 30 degrees or pi/6 radians is 1/2. And also when x is equal to 5 pi/6 radians or 150 degrees, because 5 pi/6 radians is in the second quadrant. You also see the sine of 5 pi/6 radians is 1/2. All right. See how nifty that is, how we can answer that question using the graph there. Okay. This is just showing us, ladies and gentlemen, how the graph of the sine function really is cyclical, because as we plot points on the graph, we are ultimately walking around the unit circle. And because we're walking around this unit circle and plotting points on the graph y equals sine x, ladies and gentlemen, the graph of y equals sine x we say is cyclical or periodic. Okay, and so if we've graphed one cycle of this sine wave graph, do you agree that it's possible to graph more than one period? In other words, if I was to go beyond 2 pi, ladies and gentlemen, if I was to go from 2 pi to, or 360 degrees to 390 degrees, you agree 390 degrees is coterminal with 30 degrees. So the sine of 30 degrees then would be, again, 1/2. So we would be back up here. So this graph would continue to go onward. In fact, it will continue to go onward and duplicate its form both to the right forever and to the left forever as we go around the unit circle indefinitely. And here you can see the graph of y equals sine x, ladies and gentlemen, where we now have graphed more than one period. So the graph of one period is from 0 to 2 pi. But if you want to graph two periods of y equals sine x, you would extend the x-axis out to 4 pi, because that constitutes how many trips around the unit circle when we go from 0 to 4 pi. How many times around did we go?
2.
2 complete times around the unit circle. Do you agree? And going from 0 to 4 pi. And so you can see that the graph of y equals sine x will just keep repeating itself as you go around the unit circle, putting input values into the function. Notice the sine of 5 pi half radians is equal to +1, the same as the sine of pi half radians, which is 1. Why? Because pi halves and 5 pi halves are coterminal angles, ladies and gentlemen. Pi halves is 90 degrees. 5 pi half radians is 360 plus 90 degrees, or 450 degrees. Notice the sine of 3 pi half radians, or the sine of 270 degrees, is -1, but the sine of 7 pi half radians is also -1. Why? Because 7 pi half radians is coterminal with 3 pi half radians. Notice the sine of 0, the sine of 2 pi, the sine of 4 pi are all 0. Why? Because 0, 2 pi, and 4 pi are all coterminal with each other. They're all coterminal to 0 degrees or 360 degrees. Notice if you go to the left, the sine of negative pi half radians is -1. Why is that? Because negative pi halves is coterminal with 3 pi halves, which is coterminal with 7 pi halves. In other words, -90 degrees is coterminal to 270 degrees. Okay. The sine of -3 pi half radians, which is the sine of -270 degrees, is +1. But ladies and gentlemen, -270 degrees is coterminal with 90 degrees, which is coterminal to 450 degrees, etc., etc. So it doesn't matter if you go around clockwise or counterclockwise around the unit circle. The graph of y equals sine x is going to continue to be cyclical in nature. It's cyclical because it takes for its input values around the unit circle. So on our calculator, if we wanted to graph two periods of the sine function, we just go to window. We have x range from 0 now, not to 2 pi, but maybe 4 pi. So 0 to 4 pi. Hit graph now, ladies and gentlemen. You'll see the graph of not one cycle or period of the sine function, but the graph of two periods. Do we see that there? Or to graph 4 periods of our sine x function, we can have our x-axis go from -4 pi to +4 pi. This will graph 4 cycles of the sine x function. Now you can see the graph of 4 cycles or 4 periods of y equals sine x. See how that works there? Okay. So ladies and gentlemen, this is emphasizing the fact that the y equals sine x is a periodic function, and the period of this function is 2 pi. The reason why it's 2 pi is because, stop and think, if you take any angle, ladies and gentlemen, and add 2 pi radians to it, you're always going to come back to that same angle in a coterminal sense. So any angle x added to 2 pi will always bring you back to an angle that's coterminal. In other words, 0 is coterminal to 0 plus 2 pi or 2 pi. 2 pi is coterminal to 2 pi plus 2 pi or 4 pi. 4 pi is coterminal with 4 pi plus 2 pi or 6 pi. Okay, so as long as you keep adding 2 pi to an angle, you keep coming back to the same angle, because they're always going to be coterminal angles. And for that reason, the graph of y equals sine x will keep repeating itself every 2 pi radians. Okay, so we say the period of the sine x function is 2 pi. All right, this is a formal definition of how to compute the amplitude of a function, not just for a trig function. This is for any function in general mathematics. The amplitude is always computed by taking 1/2 times the absolute value of the maximum y value on the graph, subtracting the minimum y value on the graph. So you can clearly see, therefore, ladies and gentlemen, if we apply it to the graph of y equals sine x, the amplitude is 1, because if we use this formula, the amplitude is 1/2 times the maximum y value on the graph of y equals sine x was 1, subtracting the minimum y value we found on the graph is -1. 1 subtract a -1 is 1 plus 1 or 2, and 1/2 times 2 is 1. So therefore, the amplitude of y equals sine x is 1, positive 1. To graph y equals cosine x for input values of x that range from 0 to 2 pi, again, they have a table and they have the x values spaced by pi/4 radians apart, and they crank out ordered pairs that would lie on the graph of cosine x. Notice the cosine of 0 is 1. Cosine of pi/4 or 45 degrees is square root of 2/2. Hence, this point would be a point that lies on the graph of y equals cosine x. The cosine of pi half or 90 degrees would be 0. So pi half 0 would be a point that lies on the graph of cosine x, etc., etc. So, ladies and gentlemen, graphing one period of the cosine function, this is what it would look like. This is the graph of one period or one cycle of the cosine x function. Notice its period is 2 pi. You can kind of see the period is 2 pi because look at this. The distance on the x-axis from the highest point here to where the graph achieves its highest point again is 2 pi. See that? You can see the period here. The period of this graph is 2 pi radians because we have to go on the x-axis out to 2 pi before the graph, repeats what it initially had back here at x equals 0. So 2 pi. I like to call this the distance from crest point to crest point, kind of like the high point on a wave on a lake or an ocean. Okay, the distance from crest to crest is 2 pi, so that'd be one period, we say, of the graph of this cosine x wave function here. Okay. And ladies and gentlemen, here is the graph of an infinite number of periods of y equals cosine x. Notice, why do I say an infinite number of periods? Why do I say an infinite number of periods here? What shows me that this is the graph of an infinite number of periods of y equals cosine x? Anybody? Why an infinite number of periods are being illustrated on this graph?
It would be the arrows on the end of the graph line.
Exactly. You see the red arrow here to the right and the red arrow to the left. That means this graph extends indefinitely to the right and left. Okay. And you can see how the graph of y equals cosine x keeps repeating itself over and over again as we continue to go around the circle, around, as many times as you can fathom. Okay. The graph will continue to carve out this this signature forever. And of course, we could graph y equals cosine x on our calculator very simply. All you have to do is just go to y equals and type in cosine x instead of sine x in your equation editor. Hit y equals and type in y sub 1 equals cosine x. we can leave the window setting alone. Hit graph, later on, there would be the graph of 4 periods of the cosine function. Just like with the sine function, you can see that the maximum value that is found on the graph is +1 and the minimum value is -1. So the domain of the y equals cosine x is from -infinity to +infinity here, but the range is still from -1 to 1. Doesn't matter what angle you put in for the cosine function, you'll never get any value larger than 1 for an output or less than -1. Tangent. How do we graph the tangent function? Well, here's a table of input values to graph a tangent function. They have the x values spaced up apart here. Let's see here. 1, 2. Well, they don't have them spaced apart uniformly. It doesn't appear to be the case, but they put some values in for x, and then they take the tangent of those values to get the output y values. And so therefore we have some ordered pairs that we can plot. Notice, I want to draw your attention to something here. Ladies and gentlemen, notice x ranges from 0 to 2 pi. There's actually 2 different columns here. So this table extends from this column of x and keeps going with this column of x. So 0 to 2 pi was the input values of x. Notice the tangent of x is undefined at pi-half radians. Why is that? Why is the tangent undefined at pi-half radians? Well, ladies and gentlemen, when x is equal to pi halves, we better know that as 90 degrees. And the tangent of pi-half radians by the ratio function is the sine of pi-half radians divided by the cosine of pi-half radians. But the sine of pi-half radians where 90 degrees is 1, and the cosine of pi-half radians where 0 degrees is 0. What's 1 divided by 0?
Undefined.
Undefined. So the cosine function is undefined at pi-half radians. Okay. Well, as it turns out, the cosine function, ladies and gentlemen, is not only undefined at pi-half radians, but it's also undefined at 3 pi-half radians, because 3 pi-half radians is 270 degrees. And the sine of 270 degrees is -1 divided by the cosine of 270 degrees, which is 0. So the tangent of 3 pi-half radians is -1 divided by 0, which is undefined. So the tangent function is not defined at pi-half radians or 3 pi-half radians. In order to graph the tangent function, one period or one cycle of the tangent function, ladies and gentlemen, notice we have our x-axis here, and the tick mark values start at 0 and they end at 2 pi. Hence, we've gone one circuit around the unit circle. So we will have the graph of one cycle of our tangent function. Remember, the tangent function was undefined at pi-half radians, and because of that, we put this vertical dashed line right through pi-half radians. We also put a vertical dashed line right through 3 pi-half radians because the tangent of 3 pi-half radians, or 270 degrees, is also undefined. Plotting the other points in that table that we developed, you can kind of see that the points are plotted this way. Notice you don't have any points that lie on these vertical dashed lines because, remember, the tangent's undefined for pi halves and 3 pi halves, so you will not have any output value from the tangent function when you put pi halves or 3 pi halves into it. That's why you don't see any points, red points on the vertical dashed lines. We're going to discover that these vertical dashed lines are called vertical asymptotes to the graph of the tangent function. Or we say the tangent x function is asymptotic with respect to these vertical dashed lines, in the sense that the graph will never touch these vertical dashed lines, but will infinitesimally get closer and closer and closer to these dashed lines, but will never, ever, ever, ever touch them or cross them. Okay. Now, obviously, there's an infinite number of points in between these other red points that were plotted here, because in this table back here, they just chose a finite number of input values for x. So to get the complete graph of y equals tan x, you'd want to connect these points with a smooth curve. And so, ladies and gentlemen, if you do that, you'll see that the graph of the tangent function looks like this. Now, notice they have graphed more than one period here. If we go from the x equals 0 out to 2 pi, that would be the graph of actually 0 to 2 pi, ladies and gentlemen, as we're finding out, looks like it's the graph of how many periods of the tangent function. Looks like it's the graph of more than one here. Actually, the period of the tangent function is not 2 pi, but we're going to discover it's pi radians. We'll discover that next week. Okay, so you got the graph of how many different cycles or periods of the tangent x function are graphed here. Anybody want to take a wild guess? How many periods have been graphed here? How many red graphs do you see? Haley, how many do you count? You said 5, I believe, correct?
Yeah, 5.
You are correct. They have graphed 5 periods of the tangent function here, ladies and gentlemen. 5 periods have been graphed. Okay. Notice from negative pi halves to positive pi halves, that constitutes 1 period. In 1 period here. Because the distance between negative pi halves and pi halves is pi radians. And we'll discover that the period of y equals tangent x is pi radians. Look at these vertical asymptotes. How can we summarize where the vertical asymptotes occur? How can we generalize, ladies and gentlemen, where the vertical asymptotes occur? In other words, where the tangent function is undefined in general. Anybody want to take a wild guess in generalizing for us where the vertical asymptotes occur, where the tangent function is undefined in general? Looks like we always got some sort of factor of pi halves here. Do you agree? Where the vertical asymptotes occur, some sort of a multiple of pi halves. But ladies and gentlemen, I'll give you a hint. Is it an even multiple of pi halves or an odd multiple of pi halves where the vertical asymptotes occur, where the tangent function is undefined? Odd or even multiple of pi halves? What do you think?
Is it odd?
Looks like it's odd. At 1 pi halves, tangent of x is undefined. The tangent of 3 pi halves, undefined. The tangent of 5 pi halves, undefined. The tangent of negative 1 pi halves, undefined. Tangent of negative 3 pi halves, undefined. Tangent of negative 5 pi, undefined. So the tangent is undefined at odd multiples of pi half radians in general. Notice again that the graphs of the tangent function appear to get closer and closer and closer to the vertical asymptotes as x approaches the vertical asymptotes from the left and from the right. So as the x input values approach the vertical asymptotic values from the left or from the right, the graph of the tangent function tends to get closer and closer to the vertical dashed lines or asymptotes, but the graph of y equals tangent x will never cross or touch these vertical dashed lines. They are called vertical asymptotes to that graph. In college algebra, you should have touched base with the word asymptotes, either horizontal or vertical asymptotes, especially when graphing rational functions. Does anybody remember graphing rational functions in college algebra and dealing with asymptotes? Anybody?
Oh yeah.
Does that ring a bell? Sean, you dealt with it?
Yeah, yeah, last semester I did.
Horizontal and vertical asymptotes a little bit. Okay.
Mm-hmm. Yep.
All right. Ladies and gentlemen, how would we graph like the cosecant of x? Well, let me ask you this question. The cosecant of x is the graph of, is the reciprocal of what trigonometric function? Cosecant x is the reciprocal of what trig function? Anybody?
Sine.
The sine of x. So look at, here's how we would graph the cosecant of x or the secant of x. It's really simple to graph. First of all, you have to graph what I like to call the guide function. And ladies and gentlemen, the guide function of the cosecant x function is its reciprocal function, the sine function. So in order to graph the cosecant function, first of all, you graph the sine function. So that's what they've done first. They graph y equals sine x. And let me ask you this question. How many periods of the sine x function has been graphed? How many periods has been graphed? Anybody?
2.
2 periods have been graphed, because notice x ranges from -2 pi to +2 pi. That's 2 periods, because the distance between -2 pi and 2 pi is 4 pi. That means you've gone around the unit circle twice. Okay. Now, once you graph the sine function, the guide function, you can easily graph the cosecant function. It's very easy to graph that. All you do is you put vertical dashed lines through the x-intercepts of the sine function's graph. So notice these vertical lines here go right through the x-intercepts of the blue graph, which is y equals sine x. Okay. And then, ladies and gentlemen, to graph the cosecant function is very simple. You basically have the cosecant function just touch the maximum point on the graph between the vertical lines, or touch the minimum point of y equals sine x between the vertical dashed lines. Notice there's also a vertical dashed line through x equals 0, which is the y-axis. They're not showing that, but there's the y-axis is also a vertical dashed line. So all you do is you graph these parabolic graphs. These red graphs represent the graph of the cosecant function. Notice they just touch the maximum point of the sine function or touch the minimum point of the sine function. And then the red graphs go off asymptotically with respect to the vertical dashed lines. So we can see here, ladies and gentlemen, that we have graphed 2 periods or 2 cycles of the cosecant function. If you were to then erase the blue graph or the guide functions graph or the sine x functions graph, you would be left with the graph only in red. These red curves would represent the graph of y equals cosecant x. All right. Got a question? Why? Okay. Why does the graph of cosecant x, why is it asymptotic to this vertical dashed line that goes through x equals pi? Why is it important that the graph of cosecant x is asymptotic with respect to x equals pi? Why cannot this red graph ever touch this vertical line x equals pi or cross it? Why? Give you a hint. What's the cosecant of pi radians, ladies and gentlemen? What's the cosecant of pi radians? The cosecant of x, remember, is a reciprocal of sine x. So therefore, the cosecant of pi radians is 1 over the sine of pi radians. Well, the sine of pi radians, or 180 degrees, is 0. So what's 1 divided by 0? Undefined. And so, ladies and gentlemen, the cosecant of pi radians is undefined. And that's why you have to have these vertical asymptotes as far as the graph of cosecant x is concerned. So the cosecant is undefined at pi radians, 0 radians, negative pi radians, -2 pi radians, or 2 pi radians. In general, does anybody want to generalize or summarize, ladies and gentlemen, for what values of pi is the cosecant function undefined in general? For what values of pi is cosecant undefined? Can anybody generalize?
On the even.
Even multiples. Well, wait, is it only even multiples of pi? Here we have 1 pi, correct? At 1 pi, cosecant's undefined. 2 pi, cosecant's undefined. 0 pi, -1 pi, -2 pi. Okay,
Maybe
so
just at pies at 100. How do I say this? Just pi or 180 degrees, or just half of The unit
Don't,
circle.
don't say half a pi. All right, how about if we just say any multiple of pi? Do you agree? The cosecant function is undefined for any multiple of pi.
That sounds way better.
There we go. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 6 pi, 6 pi, 7 pi, 8 pi. All right, -1 pi, -2 pi, -3 pi, -4 pi, -5 pi. The cosecant's always undefined. Okay. This is the graph of y equals secant x, and the graph to the right here was in order to graph y equals secant x. Again, first they graph the guide function, which is a reciprocal function of secant x, which is the cosine function. After graphing the cosine function, notice they have the graph of 4 periods. Not 4 periods, 2 periods, excuse me. After graphing 2 periods of the cosine function here, then again, you put vertical asymptotes through the x-intercepts of the cosine function. And then once you have the x-intercepts or the vertical asymptotes established, it's very easy to graph the secant function. Again, like the cosecant function, the graph of the secant function consists of parabolic graphs that only touch the high point of the guide function, the cosine function, or the low points, and are asymptotic with respect to the vertical dashed lines that we plotted here. Okay. If you erase the blue curve, then you are left with the graph of 2 periods of the secant function, 2 periods of the secant function. Notice the secant function is undefined at negative pi halves, 3 pi halves, -3 pi halves. Does anybody want to generalize for what input values the secant function is undefined? What type of multiples of pi halves is the secant function undefined? Anybody want to generalize this? Odd or even multiples of pi halves? What does it appear to be? 1 pi half, 3 pi halves, -1 pi half, -3 pi halves. It looks like the secant function is undefined at what? Odd multiples of pi halves? Do you agree? So the secant function would be undefined at 5 pi halves, 7 pi halves, 9 pi halves, etc., etc. Ladies and gentlemen, this is the graph here of the cotangent function. Notice it looks similar to the graph of the tangent function. How does it differ? Let's go back to the graph of the tangent function. This is the graph of the tangent function, ladies and gentlemen. Graph of the tangent function. Now, contrast that with the graph of the cotangent function. In general, what's the major difference? What's obviously different? Anybody? Graph of tangent function, graph of the cotangent function. What's the obvious difference?
Just mirrored. So
Mirrored,
just flipped.
mirrored in a sense that it's kind of like these red graphs are flipped around. Do you agree? Kind of looks like the tangent red graphs are kind of like flipped around, right, with respect to the asymptotes here. So y equals cotangent x has the graphs being flipped around. Notice the x-axis changes also. Notice the values where the functions are undefined change. For the tangent function, the tangent was undefined at odd multiples of pi halves. But now the cotangent function appears to be undefined where? For what values in general, ladies and gentlemen, is the cotangent function undefined? It looks like where it appears that the cotangent function is undefined for any multiple of pi, 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, or -1 pi, -2 pi, -3 pi, -4 pi. Why is the cotangent function undefined at pi? Let's take a look. Why is cotangent undefined at pi? If you take the cotangent of pi radians, remember cotangent by the ratio identity is really the reciprocal of the tangent function. So this would be cosine pi divided by sine pi. Cosine of pi, cosine of 180 degrees is -1, but the sine of 180 degrees or pi radians is 0. Ladies and gentlemen, -1 divided by 0 is undefined. And for that reason, the cotangent function is undefined at pi radians. In fact, the cotangent function will be undefined at any multiple of pi. Why? Because the sine, ladies and gentlemen, of any multiple of pi is always what? What's the sine of any multiple of pi? The sine of 1 pi or 2 pi or 3 pi or -1 pi or -2 pi or -3 pi. The denominator will always be 0. Do you agree? Always. That's why the cotangent of any multiple of pi is undefined. Always undefined. This last slide here gives us an overview for the domains of each of our trigonometric functions here, our 6 trig functions. In other words, the sine x and the cosine x, ladies and gentlemen, those functions are defined for all real number input values and for x. In other words, it doesn't matter what radian measurement you put in for x for the sine or cosine function, you will always get a defined real number output. The range of those functions, notice, is from -1 to 1. The amplitude of y equals sine x or cosine x is 1, and the period is 2 pi. Now, for the tangent function, ladies and gentlemen, remember, we said the tangent function was undefined for what? Where was the tangent function undefined? In general, the tangent function was undefined for any what? Any odd multiple of pi halves? Well, this is another way of generalizing any odd multiple of pi halves to say pi halves plus k pi. Why is that? Pi halves plus k pi. Ladies and gentlemen, if you let k be equal to 1, where k could be any integer, you'd have pi halves plus 1 pi or pi, which is pi halves plus 2 pi over 2, which is 3 pi half radians. Notice odd multiple of pi halves. If you let k be equal to +2, pi halves plus 2 times pi. What's pi halves plus 2 pi? Oh, that's pi halves plus 4 pi halves. Oh, that's 5 pi halves. Another odd multiple of pi halves. Okay? So in general, pi halves plus k pi, where k is any integer, will always be an odd multiple of pi halves, always. Notice the range of the tangent function is all real numbers from negative to positive infinity. Why is that? Because look at ladies and gentlemen, do you agree the graph of y equals tangent x? There is no minimum point on the graph as this red curve goes down forever to negative infinity. And there's no maximum point on the graph of y equals tangent x because the graph goes up towards positive infinity. So there would be no amplitude, ladies and gentlemen, for y equals tangent x or y equals cotangent x or y equals secant x or y equals cosecant x. There's also no, there's no amplitude for the cosecant x function because there's no maximum point because these red graphs go up forever to positive infinity and they go down forever to negative infinity. So there's no amplitude for the tangent, the cotangent, the secant, and the cosecant functions. No such thing as an amplitude for those functions. There is periods though for those functions. Notice the period of the tangent x cotangent function is pi for the secant and the cosecant function 2 pi. Notice the cotangent function is defined for all real numbers except for multiples of pi, right? Notice the cotangent function is not defined for any multiple of pi. That's being generalized here in this table. The domain of the cotangent function is all real numbers except multiples of pi. The domain of the secant function is all real numbers except what? Except odd multiples of pi halves. The domain of the cosecant function is all real numbers except multiples of pi, right? Here's the cosecant function. Notice cosecant function is not defined for any multiple of pi, 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, all right? So this table you might want to, just kind of study over, ladies and gentlemen. That's a very valuable table. It not only gives you the domains and ranges of these functions, but it gives you the periods and also indicates the amplitudes here. So a very useful table there. All right. So ladies and gentlemen, your classwork today, pretty simple. Here it is. I want you to graph one period of y equals 2 sine x. In other words, I want you to make a table. I want you to let x be equal to 0, pi halves, 2 pi, 3 pi halves, and 2 pi. I want you therefore to put all these values into y equals 2 sine x, indicate what the y value would be, plot the ordered pairs in the xy plane, and then connect them with a nice smooth curve. I want you to indicate to me what the amplitude then is of y equals 2 sine x. After having graphed y equals 2 sine x, I then want you to graph y equals 2 cosecant x. Ladies and gentlemen, this is a very simple matter once you have graphed the guide function. It should be very simple then to graph the cosecant function. Go ahead and do that. You can look at your notes. You can look at the okay, see if you can do that, ladies and gentlemen. Graph those functions there, just one period of each, okay? I strongly recommend you make a table of input and output values first, so you can, crank out your ordered pairs first and then plot the ordered pairs and then graph the functions. I will make this PowerPoint presentation available. I will put it in the same location where I put my Zoom lectures. Okay, so I'll try to do that while you're working on this.
Mr. O,
Yes.
I wasn't sure if you saw, but I sent you an email